Good morning, everyone, and welcome to this series of lectures entitled Chemistry, a hand outstretched to society, which brings together different topics related to chemistry and also chemical engineering and biochemistry. Today, we are going to attend the ninth talk of this semester, and the speaker today is a pleasure for me to introduce Sara Cembellín. Sara Cembellín is a professor from the organic department, from my department, and the title of the talk would be How to Perform Sustainable Chemistry with Transition Metals. Maite always comments when present this talk that we have chosen this format, this online format, instead of face-to-face, because when we started with this cycle of seminars, of course, the pandemic situation was much worse than today. And we have another advantage. It means that we can record the talks and we can see the talk if we want today or within a week or whatever. In addition, we do this talk in English in order to disseminate the scientific content all around the world. It's time also to thank the agencies supporting this idea. Of course, the Spanish Society of Biochemistry and Molecular Biology, the Royal Society of Chemistry, the Madrid Sectorial and the Vice Rectorate for Research and Transfer. Of course, we have to thank the Fundación General UCM for the support, for giving us the opportunity to organize this talk. You know that this is almost the very last talk will be on June the 2nd. Each seminar will be announced at the beginning of the week, including the link to the registration form. And I don't want to talk anymore because it's not my time, it's the Sara's time. And before the Sara's talk, it's time for Teresa to give a short introduction to Sara. Teresa, it's your time. Enjoy the talk. Thanks. And we are looking forward to hearing your talk. Sara, thank you.
Thank you, Luis. And thank you, everyone. For me, it's a real pleasure to introduce Sara. I knew her in 2011 when she did her final year degree project in our research group. In that same year, Sara finished her bachelor in chemistry with one of the highest marks in Spain. After, she studied a master in organic chemistry at the same university, and then she obtained a predoctoral fellowship, a FPU grant, to start her PhD under the supervision of Professor Benito Alcaide, Professor Pedro Almendros, and my own supervision, working on catalytic method of cyclization transposition of alkenes with transition metals. Along her thesis, she could also perform a predoctoral stay in the group of Professor Ben Feringa, Nobel Prize in Chemistry in 2016, at the University of Groningen, studying new catalytic method using organolytic reagents. Next, she was awarded with an Alexander von Humboldt postdoctoral research fellowship and joined the group of Professor Frank Glorious at the University of Münster in March of 2017. There, she carried out a research based on metal-catalyzed CH activation strategies. In November of the same year, she received the second Real Sociedad Española de Química Reaxis Young Researcher Award, and in April, she came back to Spain with a Juan de la Cierva grant to join the group of Professor José Alemán at Universidad Autónoma de Madrid, where she started to work on the field of photocatalysis. In October in 2020, she got a position as Profesora Ayudante Doctor at Universidad de Alcalá. And finally, in July of 2021, last year, she came back to Universidad Complutense with a permanent position as Profesora Contratada Doctora. Actually, we work together in organic chemistry department in our group of Química de sistemas insaturados y heterociclos bioactivos. During all her time as researcher, she published 21 works, and she also has participated in more than 20 national and international conferences, and is continuously involved in activities of popular science like Week of Science, Mind the Lab, and European Researchers' Night. And now, Sara, is your time, so you can tell us about your most recent research.
So, okay, first of all, I want to thank Teresa for her kind introduction, and of course, all the faculty, the members of the Faculty of Chemistry, for giving me the opportunity to be here today giving this talk with the title, How to Perform Sustainable Chemistry with Transition Metals. Today I will talk about the chemistry that I was performing since I left the Universidad Complutense when I finished my PhD until I came here again in July 2021. And I will mostly focus in the chemistry that I was doing during my postdoctoral studies at the University of Munster in the group of Professor Frank Glorious. So the first thing that we have to say about this talk is that nowadays there is a general and common interest between the scientists to develop more sustainable processes. So we as chemists have to develop new chemical transformations that are efficient, economical, and also environmentally friendly. If we focus our attention in organic chemistry, I select here two molecules, the cyprazodone and terbinafine, that they have both biological activity. Cyprazodone is a commonly drug in the treatment of schizophrenia, and terbinafine has antifungal activity. As you can see, even if they have different heteroatoms and also functional groups, the most abundant bond in both molecules is the carbon-hydrogen bond. Like here you can see, yeah, then like 20 carbon CH bonds in cyprazodone and all 23 in terbinafine. So there is a very high number, even if they are like more or less small molecules. So you can guess that one of these such ideal transformations that we are looking for is the, is the direct functionalization of this carbon-hydrogen bond. So if we compare this strategy with the conventional approaches, in contrast with the traditional methods that they need a prefunctionalized substrate, now we can functionalize in a direct way this CH bond. So we can reduce the number of the steps of the reaction, the waste produced, and also the amount of the reagents that we require. But as I said before, we have a problem that the organic molecules have a lot of CH bonds. So how we can select the one that we want? So for this, we use the strategy of the directing group assistant. So here in our substrate, one atom of a group of atoms can act as directing group, so they can coordinate the metal and guide its insertion in a selective way. So in the carbon-hydrogen bond that we want. Here I show you here the ortho position, but also it's possible to do in the meta or the para, but normally the ortho is the most common one. So later, this metallocycle can be chained for the functional group that we want, developing like this a totally radioselective protocol. The problem with this is when we started with the methods of the CH functionalization, and they were always like used for the unfighty transition metal, like palladium, platinum, rhodium, that, as you know, they have several drawbacks. However, in the last year, there are more and more examples that they started to employ first-row 3D transition metal as cobalt, manganese, iron, or nickel, that they have great abundance, low cost, low toxicity, and sometimes also a unique and powerful reactivity. If we focus our attention in manganese, we have to say that it's the 12th most abundant element and the 3rd most abundant transition metal in Earth, and also is an essential trace element for life. If we check its price and its toxicity, we observe that the price is really good, even like better if we compare with other 3D transition metals, and also its toxicity is only improved by the iron. Due to these good characteristics of the manganese, in the literature there are a lot of catalysts that they have this metal. I am going to show you here the most important types. We have, for example, the high valent manganese species, that they are used a lot in Christina White chemistry, and they normally perform homolytic cleavage of alkyl CH bonds. We have also the manganese pincher complexes used a lot in Matthias Beller chemistry for doing hydrogenation reaction. And also these manganese carbonyl complexes, they are very cheap and also very available, and they normally are used for the functionalization of alkenyl and aryl CH bonds. With this kind of catalyst, these carbonyl complexes, that is the ones that we are going to use, in 1970, they discovered that the manganese activation was possible. They isolated, like the group of Stone, this manganocycle that they discovered that is more or less stable in an easy way. However, we didn't have any example of manganese CH activation in a catalytic way until 2017, when Kuninobi and Takai described the first example of this chemistry with the insertion of aldehydes in aromatic rings having this heterocycle as directing group. We have to wait another 6 years until one and co-workers described the second example with the radioselective insertion of terminal alkynes in phenylpyridines. Since this moment, they start to appear a lot of contribution of different groups as Ackerman, Lee, Fairlem, and also Glorious. But it's important to say that when I joined the group in March 2017, there were only 18 examples of this chemistry. So we thought that it would be a very interesting topic to try to develop new chemical transformation and synthesize variable organic molecules. And we could perform our goal, and in the next year, we will develop the synthesis of important molecules, for example, isoquinolines, dieteroaryl methanes, alkynes, beta-aryl ketones, or also complex molecules using this manganese CH activation strategy. Today, I will focus only in the reactions that they involve the insertion of alkynes. So how this story started? We decided to synthesize important heterocycles, and we focus our attention in isoquinolines. Why? Because they are present in a lot of bioactive molecules and also natural products. For example, I show you here in this slide the papaverine or the noscapine, that they have important antipasmotic or antitussive properties. So when we check the literature, we observe that if we check the methods that they use an aromatic ring and an alkyne, there were several examples with a lot of metals, palladium, rhodium, ruthenium, and also even manganese, but they have a lot of problems of radioselectivity when they use internal alkynes with different moieties. So normally they obtain mixtures of the two radioisomers that they are possible in the reaction. So at this point we thought, okay, maybe we can also insert another like directing group also in the coupling partner in the alkyne that we call here Traceless directing group, that can guide the metal and guide the insertion of the alkyne. So this is going to be totally radioselective, and later is going to be disappear, like giving our isoquinoline in like an only one example, one isomer. So how we can try to do this approach? So we select as model substrate this compound 1A that has an imine group as the directing group of the aromatic ring, and different alkynes with different directing groups in this part. We evaluate this important, and we observe that the best result was obtained with the propargyl carbonates. Also, we could perform the reaction with also the bulk protected one, and with acetoxy or also with the free hydroxy group, we didn't obtain very good results. After this good result, and after a slightly modification of the reaction condition, we could also study the scope of the reaction. So we were very happy to see that we could have like different moieties in the aromatic ring, like electrodonating, electrowithdrawing. I'm not going to show you here all the examples, only the most representative ones. But also we could check that the modification in that kind was possible. We could introduce heterocycles, also alkyl chains, and even cycles. And of course, we checked that we could use a starting material, the aryl ketimines, and also imidates. And of course, that the reaction was not limited to the aromatic rings, but also heterocycles. For example, here, this thiophene that I show you here in the slide. Encouraged by these promising results, we wanted to study also if the reaction was possible also with secondary and primary alkynes. Yeah, we checked that, of course, yeah, we could do this, and we obtain a different variety of isoquinolines with very good yields, as you can see, between 60 and 90% of yield. It's very important also to remark that we could synthesize these 4 isoquinolines, that you can see that their structure is not very complex, but it's the first time that they could be isolated as a single isomer doing CH activation strategies. So we also wanted to know a bit more about the mechanism, that how we can perform like these isoquinolines. So we decided to set up the reaction with another starting material that cannot have the cyclization step. So we took as the substrate this pyridine indole 4A with our standard conditions. And we obtained the formation of this alene 5A, depending also of the nature of the moieties. We performed the reaction also with the amine 4B and the same conditions, and we observed the formation of the diene 5B that we suppose that comes from the isomerization of the alene that is formed in situ. These 2 experiments show us that it's very probable that we have an alene intermediate in our reaction. Also, we observed when we set up the reaction with this enantiomeric alkyne that we didn't have any transfer of chirality. So with this, we can also assume that the last step of the cyclization is due to a nucleophilic attack. With all of this information, we also could propose a mechanism that you can see here. It will start with the CH activation process between the starting material and the manganese. We did also some kinetic mechanistic studies, and we observed that this step, in this case, it will be the rate determinant step of the reaction because of this 1.62 kinetic isotopic effect. Once we have this manganocycle, it will happen the coordination of the carbonate, this oxygen with the manganese can be coordinated, and the alkyne insertion, that of course is going to be totally radioselective due to this coordination of the carbonate. Finally, it will happen the beta oxygen elimination doing this intermediate that we said before, no, this alene, that finally can happen a cyclization process that can happen from like the nucleophilic attack of this nitrogen group to the alene. So with this also we wanted to check the applicability of this method, and we tried to synthesize some natural products of bioactive compounds. We could synthesize this compound 3Z with 45% of yield using our protocol. That also is an important precursor of this molecule, and of course like this molecule PK that has a very good activity in the antitumoral cancers. Also, we could check and we could synthesize also demoxaverin, that is an important drug for gastrointestinal disorders, with our method in a very simple way, only one step, having also a 59% of yield. So with this, we decide, okay, can we also synthesize isoquinolines, not only isoquinolines? Okay, the answer is yes, we could do it. We will synthesize a variety of isoquinolines. I show you here only 4 in a 2-step procedure without isolation the isoquinoline intermediates. And we also wanted to try to do isochimerins, but in this case, the answer was no. We tried to develop the same method, but in this case with carboxylic acid as starting materials, but the reaction with manganese failed. But thanks, we also try another methods, and at the end, we also develop another protocol with ruthenium catalysis that I'm not going to explain here in detail. So with this idea of the introduction of the directing group in the coupling partner in the alkyne, we could develop an important method to synthesize isoquinolines with very good yields and also a lot of examples, and the most important things with total radioselectivity. So at this point, we decide, okay, can we do also the same with terminal alkynes, but not the normal ones, like high complex terminal alkynes? So for this, we select these benzosacinones, that is molecule 8, that they were present in a lot of examples in the literature with copper catalyst. So they say that with copper, you could form these metallalynidine species that they have an electrophilic center in their extractor. So they can suffer the nucleophilic attack by like different compounds, for example, this indole 7A. So they perform propagylation reactions as the one that I showed you here in the slide. So we thought we can do the same, but with our manganese, maybe, and we can have this manganocycle with the indole, and in our case now is going to be the insertion of the alkyne. So total different chemistry than the one that it was described before. We tried the reaction and we were very happy to see that we obtained this heteroaryl methane 9 with very good yields. I show you here that we could obtain the indole, like the compound 9AA and compound 9AB with around like 80% of yield when we applied our manganese chemistry. With this, we decide also to see, okay, how can be the scope of this reaction? Is limited to the indole. We observed at the beginning that we could also have different moieties in the indole core, but the most important thing is that we observed that it was not restricted for the indole core. We could realize the reaction in different heterocycles, as thiophene, benzothiophene, and also pyrroles. And of course, we also check that we don't have to have this amino group like free. We have to have like tosyl group that is protecting and have different compounds, for example, the one that I show here, that permit that now we have also different substitution also in the complete partner A's. Of course, this extractor was also totally confirmed with the X-ray of the compound 9AJ. We also wanted to show the applicability of these heteroaryl methanes, and we could remove the directing group, this pyridine group, with magnesium and methanol, and we obtained the compound 10 that is a very important chemical sensor and ligand moiety. And also, it can be the precursor of this antitumoral compound. We also could synthesize different polyheterocycles, like the one here that I showed you here, that is the 11, that has a lot of importance in material science. If we want also to know how we can, how we did this reaction, how these heteroaryl methanes they were formed, we can explain that with a similar mechanism that is we will start again with the CH activation process. In this case, this is not the rate determining step of the reaction because of the kinetic isotopy effect. But we have again this manganocycle that later can suffer the insertion of the carbamate. At this point, we have to say that we also observe a secondary product in one of our reactions, that is this product, the 13, that we assume that comes from the nucleophilic attack of the nitrogen to the allene, and later like the coupling with another molecule of allene. So with this, we can also guess that we have another allene intermediate, that it can be this intermediate 3 that occurs via beta-oxygen elimination. When we have this allene, the reaction can proceed by the path A, that is can happen the allene insertion and later the protonation, or for the path B, that is the same, but before it will be the protonation and later the cyclization step. So with this, we could also develop a synthesis of important molecules, these heteroaryl methanes, that also with good yields and also total radioselectivity. So at this point we said, okay, so what is going to happen if we have 2 alkyne units? We wanted to check also what is going to happen with the insertion of the 1,3-dienes. So in this case, we have to say that the 1,3-dienes, they were used as coupling partners in CH activation reaction, but its use was not super developed. We saw several examples, but all they were limited with rhodium or cobalt, and they are restricted to annulation reactions. When we check the manganese catalysis, we observed that the group of T in 2018, they developed a very elegant transformation that is the hydrogenation of these 1,3-diene alcohols. The problems of this reaction is that it was limited to 1,3-diene alcohols. The boronic acids were required, and also they used a non-commercial manganese catalyst. So at this point, we thought that maybe our strategy of the manganese catalytic CH activation will be a better approach for having these 1,3-dienes. But as I commented before, in the manganese chemistry, when we have an alkyne with different moieties, we can have problems of the radioselectivity unless we put another directing group in this coupling partner. Also, we have to take in account that the use of 1,3-dienes imply further challenges. So for example, that we have to control the chemoselectivity between the two alkyne units. We have to control the region, the stereoselectivity of the migratory insertion, and also the selectivity between the mono and the defunctionalization. So with all of this information in mind, we try to set up the reaction, and we chose the pyridine indole again for developing the reaction, and this 1,3-diene with TMS groups with manganese catalyst. We were very happy to see that we obtained only one radioisomer, this compound 16AA, when we performed the reaction with manganese, sodium acetase as base, 1,4-dioxane as solvent, and performing the reaction at 90 degrees. We tried different solvents, but we didn't improve this result, that it was very good already. And we also performed some control experiments, as for example, we removed the manganese and we observed that it was totally inactive, and we removed the base and we observed that the yield also dropped drastically. We also wanted to check if there were more metals that can develop this reaction, like trying rhodium, cobalt, or ruthenium, that they are also very common in this CH activation reaction with alkynes, but we observed that they were totally inactive in our protocol. So this also highlights the important role that manganese play in our methodology. So with these, once we have the optimized reaction in hand, we decide also to study the scope of the reaction, and we could check that, again, we could put different moieties in the indole core, but more important is that we also could change the directing group, and we can use now also the pyrimidine group, that is a more easily removable directing group. We could also set up the reaction with different heterocycles, like thiophene and furans, and also in normal aromatic rings, as the one that I show you here. And also, we could show the applicability of this reaction with the totally selective functionalization of natural products, as for example, the melatonin or the tryptophan. So once we have also these good results, we decide, okay, what is going to happen if we change this TMS group? Is it mandatory for the reaction? We saw that no, that we could also use different alkyl chains, and we obtained the corresponding enines with very good yields. And at this point, we also decide to give a step further, and we decide to try what is going to happen if these two moieties in the alkyne, they are not the same, with unsymmetrical dienes. We were very happy to see that we obtained only one of the 8 possible isomers in this reaction. We obtained these enines from 16AA to 16AA with very good yields, and only one of the products or the final products of the reaction. We could also synthesize this molecule 16Al that has 3 consecutive insaturation in the extractor, that can also have a lot of importance in material science. It's important also to say that sometimes when the moieties they were very similar, in this case, for example, the cyclopropyl or butyl chain, that we could have a bit of the 2 isomers, in this case, this mixture with 88% of yield. But more important is to say what happened when we try 1,3-diene alcohols. We obtain the corresponding enine, the 16AM, but also we observe the formation of the furan 17A. We thought that the formation of this product comes from the nucleophilic attack of this oxygen group, and later a dehydration process. So we super happy with this interesting result. We decide also to try to develop a new protocol to try to synthesize furan. And we could do it. We only modify slightly the condition of the reaction, and we could obtain these furans, in this case with moderate to good yields. So we could do it with oxygen, so why we cannot try with also nitrogen? We try the reaction with 1,3-diene amines, and we could synthesize pyrrhos in a very good yield. So once we have this, we try to also say something about the mechanism. We can say that the reaction will start again with the CH activation process. We have this manganocycle that later here can be processed the alkyne coordination and the insertion. This insertion now is again radioselective, and here we think that is because the second alkyne unit act also as the directing group of the process. Trying to prove this, we set up the reaction with a monoalkyne, the one that you saw here in the slide, and we obtain a mixture of alkenes as the final products. So with this, we can say that, of course, the second alkyne is very important for the radioselectivity of the reaction. Finally, will happen the protonation, and we will obtain our 1,3-enines. In this project, also, we decide to test or to try to apply two assessment tools that they were developed in the group of Frank Lorios. The first one is the additive-based robustness screen. That it is a screen that is used for the transformation to check how robust they are, this transformation. For this, we can set up the reaction with the optimized conditions, and also in the presence of sub-additives. These additives, they are the ones that I show you here, 15 additives that they have different functional groups. For example, amines, alkynes, alcohols, heterocycles. And with this, we can check if the reaction tolerates this functional group in the media of the reaction. We observe the result that you can see also better in the graphics. And here we can evaluate how the yield of the reaction change in the presence of the additive, and also if we can recover or not the additive. As you can see here, as with this green and also this table here, that our reaction is very robust. You can have the product with very similar yields to the standard one, except when we have alkynes, of course, that they can use as starting material, also pyridines, that they are also again in the starting materials, heterocycles that of course can coordinate the manganese, and also these amides that also can do the same. But the rest, they didn't have any problem in our reaction. The second tool that we used was the reaction condition-based sensitivity assessment. It's also a process that give information about how reproducible is our reaction. So in this, we can perform the reaction, but we modify slightly some conditions. In this case, the concentration, the water, oxygen, temperature of the stirring. And we observe how our yield change with these slightly modifications. We have this result that you can see better in this diagram. And we observe that our reaction also is very reproducible. And the most important problem is when this level of water is increased, that we can see that our yield decreased 70%. So with this, we also wanted to show why our 1,3-enines are important, and we could develop some transformations. For example, we could synthesize this carbazole with gold catalysis. We could also perform mono or bis decylylation of the product, depending on the reaction conditions that we use. And we also could realize like a sonogacira coupling, and we could introduce an aromatic ring in the final product. So with this, also we will check that we could insert 1,3-D-ions with our manganese catalysis, and we could synthesize not only 1,3-enines, but also some heterocycles as the furan and the pyrroles, also with total radioselectivity. So the last thing that we thought, okay, what is going to happen instead of two alkyne units, we have a mixture of alkene and alkyne. So we try to insert also 1,3-enines. For this, we select as model substrate this phenylpyridine 21 and this 1,3-enine that is very easy to synthesize in a two-step procedure, also with our manganese catalysis. We were very surprised when we observed the final product of the reaction is this complex extractor that's called indolysino 3,4,5-AB isoindoles that they normally call inis, that is easier. And we observed that we could synthesize 3 different inis, the ones that I showed you here, without moieties, with a methoxy or a chloran. But the problem was that we couldn't improve the yield, and in all the cases, our best yield was 20%. But it's also important to remark that these products were the only product of the reaction, and we could also isolate these compounds in a very easy way with a chromatographic column, also recovering the starting materials. So with this good result that is promising at least, and also with the importance of the inis, we continue with this project. It's like the inis are very important because, first of all, if we check the literature, there are not a lot of ways to do their synthesis. They are here the 4 most important pathways to do the INIs, and they have something in common, that is that all of them, they use unstable or not easily accessible starting materials, and they have also a very restricted substitution in the aromatic ring. If we take into account this with the importance of the INIs, that they have like very important fluorescent, they have high quantum efficiency, also with emission colors in the blue to green region, and also they have a very good characteristic, that is that they have easily tunable HOMO and LUMO levels. So for all of these, they have very good candidates for OLEDs and sensor device fabricators. With all this important, we decided to continue the project, and at the end, we could synthesize not only these 3 compounds, but also another 3 more, with also halogens group like bromine or iodine, and also this additional aromatic ring. In all the cases, we couldn't improve the yield. So trying to improve this reaction, we also decided to do some mechanistic studies. We synthesized the manganocycle 24, and we purify it because it's very stable. And we set up the reaction with this manganocycle and our starting condition, our standard conditions. So we could obtain the INI 23A with 20% of yield. This experiment showed to us that in effect, our reaction is also a manganese catalyzed CH activation reaction. Also, we tried to develop the reaction with other metals. We tried palladium, cobalt, rhodium, and ruthenium, but we observed that they were totally inactive in the reaction, and the reaction could proceed only with manganese catalyst. So with this, again, we saw the unique reactivity of the manganese, but we didn't obtain more information. So we decided at least to study the compounds that we have, because they were very important. So we decided to do an study of the structural properties, and we obtained the X-ray of the compound 3C, and we observed like its planar geometry, and also this X-ray corroborate the aromaticity of the compound. Also, all the data were in accordance with the single previous report of these compounds. We also decided to do a photophysical study in collaboration with Professor Christian Strasser from the University of Münster also. They recorded the absorption spectra and also the excitation and emission spectra. And we could observe that the products, they have a blue sheet caused by the substituent. In the case of the methoxy group, also this blue sheet was bigger than in the case of the chloride. Also, we did some DFT calculation with collaboration with Professor Nicholas Stinit, and they observed that theoretical absorption spectra matches perfectly with experimental ones. And also they did some calculation for the HOMO and the LUMO levels of our compounds. With this, they confirmed that the lowest excited states are placed in the indolysine core, in the core of the molecule. And the moiety modifies the HOMO and the LUMO band gap. So this explains why we saw this blue sheet in the spectra. So with this, we also could develop a method that in this case, we couldn't have a lot of examples and with very good yield, but we obtained very important molecules with very important photophysical properties. So with this, I think that I hope that I convinced you that the powerful of this manganese catalyst. I show you here all the examples that we did. The only ones that I didn't show you is the formation of the alkynes or the beta-aryl ketones, that we did it with insertion of alkenes and diazo compounds instead of alkynes. And it's important to say that now in May 2022, that we don't have anymore like only 18 examples. We have like more than 100 or 200 examples of manganese CH activation reaction. But okay, the question is, what is next, no? What are you going to do now? So I explained to you here all the reaction with first raw metal catalyzed CH activation. But the problem with this reaction is that they have a main drawback, that all the reaction I perform with very high temperatures. So this for the sustainability is not good. So how we can improve this? We can improve with the merging like this CH activation with renewable energy sources, as for example, the light of the electricity. In the literature, we could see already some examples of this merging like photoredox catalysis with metal CH activation described for several groups, for example, Sanford, Ripin, or Ackerman, but not with like first raw metal, like a lot of them they have with precious metals. And also some examples with electrocatalysis and metal CH activation developed by Ackerman, May, or Ley, but in this case, yes, with some first raw metals. So I think that this is a very important topic to try to start a new research. So for this, I did my second postdoctoral stay in the group of Professor José Alemán in Universidad Autónoma de Madrid, and I started to work with photocatalysis. There, I described like a very sustainable method to synthesize isothiols, starting from these iminoxy acids and also using only a photocatalyst, acetone, and also blue LEDs. So after this, I also joined Universidad de Alcalá, and there I had the pleasure to also start my knowledge about electrocatalysis in the group of Professor Belén Batanero. So now I think that I can also join this knowledge of photocatalysis and electrocatalysis with the CH activation with first raw metals. And I hope that I can develop here in Universidad Complutense a research base of these like CH activation reactions more sustainable with renewable energy sources. So with this, I want to thank all the people that helped me in all these projects, that they are here. Also, of course, Professor Frank Glorio for his support, and Alexander von Humboldt for the financial support. Of course, also, I want to thank the group of Professor José Alemán, the group of Belén Batanero, and of course, all my group, Grupo de Química y Sistemas Saturados y Heterociclos Bioactivos, where I did the PhD, and now I am also part of them. And last but not least, thank you all of you for your attention. Thank you very much. Okay.
Thank you very much for your great talk. At least to me, have convinced about the use of manganese. So it has been a good talk. And now, if someone has any question, for example, Diego Garcia has wrote a question about your last project with manganese. Do you have an explanation about the low yields that you obtain?
Yeah, this is a very important question and also difficult to answer. Yeah, we don't have it. We try to perform a lot of studies. We think that is something of the cycle that is not working well. We try also some reaction with more like amount of the manganese, trying to check also with stoichiometric amount of manganese, and the reaction was not better. Also, we try to add in different times the manganese, trying to check if the manganese is destroyed in the media, but we didn't obtain better results. So we are also trying to also do more mechanistic studies, trying to study the mechanism of the reaction, because we think that the answer is there, but we don't know why. It's a low conversion, nothing more. We don't have any other products.
Well, I have.
Teresa.
Yes.
May I make a question? Like
yes, you can.
Not like a sort of moderator or whatever. So yes. Like a researcher quite out of this topic. For me, it's amazing. Sara is amazing. It's really nice, all the studies you have done, and many studies with many experimental conditions. So I have a couple of short questions. The first one would be related with the Diego's question. So you have a very low yield. So what's about the rest of starting material? But you already give a sort of explanation about that, because you have a sort of the composition, but you don't observe any new product.
No, this project also is the first molecule that I obtained when I joined the group of Frank Glorious, and I was working with it like the 2 years, sometimes as my secondary project, of course. But we try to do a lot of things. We don't know. We don't have another product. We have only the fluorescent compound, that is the INIS, that you can see perfectly also in the column in the reaction, because it's very fluorescent. And you can obtain again the pyridine, and also sometimes also the coupling partner, that is totally like unaltered. So it's like a problem of the conversion. But yeah, so we can think, okay, it's the manganese that is destroying, that we know the manganese sometimes decompose, but in the other reactions, no. And also if you put more manganese, the reaction is not working. So yeah, it is also a very interesting project, but it's a pity that we couldn't do more. But I don't know if it's possible to do more.
And thank you, Sara. And the next question is a sort of philosophical question. So do you think that we are going to have a comparable manganese chemistry with nickel chemistry?
Yeah, this is a good question, and I know that I like a lot manganese and I had very good results with it, but I don't think so. The problem of manganese has unique reactivity, and it's true that I realized some reactions that if you try with palladium, you try with nickel, they didn't work. Of course, with changing the condition, no, like better conditions for the other metals. But it's true also the manganese is very specific. It's working only with some atoms, with some coordination. So if you change slightly, like, I don't know, its preference, it's not working anymore. So of course you cannot compare with nickel. Nickel also, I like all the metals. There's not a problem, but it's true that manganese is very good. But of course, it's always like, I think that there is a space for other metals, and nickel, I think that is more versatile. I think so.
Then you have a nice opportunity to change this view.
Yeah.
Please go ahead. Thanks,
yeah,
Sara.
no problem. I did a lot of with gold and palladium, manganese, and now I can do another thing.
Okay, thanks, Sara. Nice talk.
And Sara? Yes.
Sara is frozen.
Yes, frozen. Could you hear me?
I think that,
yes, now, yes?
Yes, I can hear you.
Okay,
I think that
okay.
I have slightly problems with the connection, but it's good.
Now we can hear you. So I have two curiosities. Compare with other metal catalysts, for example, palladium. You use a high relative loading of manganese. Is possible to reduce this amount? Less than 10 mol%, that is the normal.
Yeah, we can, if this is true, it's also like a problem of some of our reactions. I saw you here also that the standard conditions, but some of the projects, I think the first one and the second one, we could use also one, even like 5 and even 1% of the catalyst. It's true that the yield was a bit worse, but we could do it. But for example, in the third project, we tried to do, and the yield was like decreasing a lot, no? So the manganese, the problem is that sometimes, and I said before, sometimes it decomposes. There are like some studies of the group of Erlam that they also detect some clusters of manganese in the media. So we know that some slightly amount, but some is decomposed. So we think that is the reason that we cannot like decrease so much the catalyst loading of the reaction.
Okay, thank you. And just the last one, curiosity. Can you use other directing group without nitrogen atoms in the manganese catalysis?
Yeah, this is also the thing that I told Luis, no? Manganese is sometimes is restricted to some conditions, and one of them is this. There are like some articles that they use carboxylic acid with manganese, so we know that it can coordinate it, but it's true that it's not very favored. So normally all the reaction with manganese, they have imines, pyridines, pyrimidines, but not a lot they have carboxylic or oxygen groups, no? It's possible, yes, but it's more difficult to achieve, no? Manganese has I don't know, I think that it prefers to join with more like strong coordinating groups than the weak ones.
Okay, thank you so much. I have seen another question in answer, and Jose Ignacio asked to you if rhenium or even technetium show a behavior as manganese.
Yeah, technetium I never tried, so I cannot answer this question, but rhenium yes, and also sometimes the reactivity is similar, but not always. We tried like, I don't know if all the projects, but I think more like 2 or 3 of the ones that we did in Germany. Sometimes we could observe like a bit of reactivity, but not as good as with the manganese, and sometimes it was inactive at all. So they have similar reactivity, but not the same. So I think manganese is more powerful in this kind of chemistry.
Okay. And just for finish, because I was thinking about your last project of INIS, do you have some information about the mechanism? Because I don't remember, but I think that you didn't tell us about the mechanism of this part of the research.
No, I didn't say anything because we are also studying this mechanism now. We think, no, we have like the assumption that we have like some kind of cumulin intermediate. Okay, these 139s, they are precursors of cumulin, so 3 cumulins, no? So you know that we are very expert in unsaturated chemistry. So I was trying to do some kind of cumulin when I tried the reaction. So maybe we don't have this intermediate, we have something like similar that after the seed activation, maybe it's going to be like some unsaturated, accumulated like double bonds, but we cannot say, no. We try to do a lot of assumptions with this, but we are still studying about this mechanism.
Thank you. And Jose Ignacio has a new question about the previous one. I don't know if you can read. He asks you, there are not even differences related to the yield about using rhenium for sample instead of manganese?
Yeah, maybe I didn't explain correctly, but yes, we have like a lot of difference between manganese and rhenium, and normally in our cases, that sometimes rhenium is active, but not so good as manganese. Maybe, for example, if we have like 90% of yield in the standard conditions, with rhenium we have like 30, and sometimes 0. So it depends of the reaction. Yeah.
Okay. So if anyone has more questions, and if not, we can finish with this webinar. Thank you so much, Sara, again for your great talk. And I hope you have here very, very excellent result as in Germany. I'll see, because I'll try to be with you.
Thank you.
And Luis, for closing the webinar, I think you have to talk.
Okay, thanks, Teresa. Well, I have to finish the webinar. Of course, once again, Sara, thanks for the very nice talk, for the very stimulating talk. Thanks, Teresa, for moderating the session, the webinar. Thanks to all the attendees for participating and for the question, Jose Ignacio and Diego, of course, all of them for sure. And please take care of the next and very last seminar. It will take place on June the 2nd, and the title of this webinar would be Control of Wetting Properties to Design Low Fouling Surfaces. Take care. Thanks, Sara, once again. Thanks, Teresa, and see you.